Hello and welcome. Here we are in lecture 9. So you can see from the title, today's gonna be about testing. And testing is one of those things that's actually really, I think stop before I forget, really important. So uh, I'll get to more motivation testing in just a minute, but to kind of fit this into the broader scheme for how we organize content in this course, as you kind of seen, we did what we could to close the loop early. On lecture 2, we actually had Chisel running, and even to actually animate, we had even had a really tiny test case, right? And since then, we learned a little about the tester, and we learned more about Scala, a little more about Chisel, and now we're gonna come back and learn a lot more about testing today. And actually, today won't be the end of testing. We'll actually come back to it again in a few weeks, talk about formals. It's kind of this approach of kind of getting a little more in everything all at once, and so we're kind of just making your tour around various functionalities and getting more and more depth as we go. And so today's gonna be about testing. So let's get to it. Um, so what are we talking about? Well, number one, we talk first to try and really motivate the importance of testing and some just general strategies for testing. Should we think about testing? Some of this is particular to Agile hardware design. Some of it's just more general about testing, which may be applicable in your purely software projects. We'll start simple. We'll test a purely combinational hardware first. Then we'll get some better organization with Scala test. And finally, we'll move on to a stateful element, which is, in this case, we're using a queue as our example. So, okay, you can call them load a notebook, sure. Oops, sorry. Uh, but the key thing is the next slide, which is more about the why, right? So why are we concerned with testing? Well, first off, why doesn't we want your hardware doesn't work, right? I think this is overlooked a lot of times when we're building systems. We get so involved about building something that's important to us, and that's why we're building it. But the truth is, other people don't really care about it unless it works, right? So it's really important that it works, especially with hardware where we have situations where it's not just a design, but often if you want to manufacture it as an ASIC, right? That's, once it's made, it's immutable, right? So it's really important it works, right? Um, and so when it comes to testing, it's not just does it work, period, but kind of convincing people it works, right? So it's one thing to say, oh, well, it's probably correct, or maybe even is correct, but can I prove to myself it works? How do I know it's correct? How do I convince myself it's correct? And then how do I prove to others it's correct, right? So those are kind of the main things we want to get out of testing. And then one of the things we're hoping kind of change from today and hopefully perhaps change your perspective is not just testing as some sort of checkbox thing you do at the end, but also and viewing it as something you kind of do continuously as you're doing the project to help you develop it better, right? So you may have heard the term TDD or test-driven development. And this is kind of what we're going to talk about. Okay, so if I succeed today, you're going to learn a few things, right? Hopefully, you'll get some, concrete skills with, Chisel, Scala test, etc., about how to do actual testing. But what you're going to see is I'm actually going to go through some of these case studies where I'm going to methodically build up abstractions. So rather than simply just blindly writing a couple tests, we're going to try to build up abstractions infrastructure to not only make tests productively, right, make them quickly, but to also have higher confidence tests to get better coverage for tests. And that's kind of the point. And hopefully, as you kind of start getting more involved in testing and seeing all this stuff going on, can change your perspective and start you to feel of testing is kind of an integral part of development. It's kind of a key part of what you're doing, not just something you do at the end to satisfy some sort of checkbox. And yeah, we'll talk about some cool tricks we can do in Chisel and Scala to kind of make this testing easier and more fun. Okay, so in order to actually do any sort of testing, this is true of not just hardware, but anything, you actually need three things. Uh, First, you need a test case, right? What the heck are we actually going to be testing? Second, you need the right answer to test cases. In other words, okay, sure, I have stimulus that animates my design, but what's the correct response? And then third, you need some sort of way to actually execute and automate the test, right? Um, and be really clear, for example, that maybe you might say, oh, I'm testing my project. I test it by running this, design through it or run on this piece of, design, and then check to make sure your output matches this, right? If you as a human have to manually input the design and manually have to check the output, that's not really an automated test case. So maybe the test case, but it's not an automated test. And today's primarily about automated tests. So really, you got to think about all three of these components, right? So number one, like I said, where does that test case come from, right? So when you're first getting started, maybe you write some tests manually, human generated, sure. But eventually, you should change gears. Once again, talk about building productive abstractions. Make the tools do the work, right? So actually have tests that are generated by the tools, right? Rather than you having to try your best and just randomly write things out, is there some way you can have the tools help you, right? Maybe you'll learn some very classic techniques, things like exhaustive testing, something that's actually possible, directed random, etc. There's various ways to have the tools generate test cases. Then number two, just the one I think might be the biggest change when you may have seen before, or perhaps conceded before, and that is how do you make sure you have the right answer to a test? Not just a matter of having the input, but also you have to have the output you're comparing against. And so yeah, on day one, to get things going, maybe you have a human-generated test case where you, as a human, write the input, and you also write the output manually, and that's just, what is scoring against your first test case running. You know what? That's okay for day one. Close that loop, get things going, bootstrap it, great. But once you start getting things going, you want to have a more methodical, more disciplined, more rigorous, more correct way of making those responses. And so the technique we're using in this course is model generated, right? Meaning we're going to have a model that is supposed to be the correct response to the thing we're building. And so this model's not going to be necessarily hardware, right? It's usually going to be Scala code that does the exact same operation we're trying to do in hardware. So realize the Scala code that's functionally emulating what we're trying to do is often going to be much, much simpler in terms of the hardware design, right? It's not trying to pipeline things or have optimizations. It's just computing the numerical result we want to produce. So oftentimes it's going to be a lot simpler. And thus, it's easy to get this Scala model correct, and then we use the Scala model to generate the correct output to compare against. So that's another thing to kind of keep in mind. And then third and finally, as I said, we want to have this automation, right? We want to have some sort of way where we trigger this test to run, and then it loads in the correct inputs, it checks the outputs and compares them against the model, perhaps, and this is in try an automated way, right? And so there's a lot of different ways to do this, because you have to kind of consider in case of hardware as an issue of how you're simulating design, how are you generating a test case and loading it in, and how are you comparing and scripting it all. In this course, we're using a methodology kind of pitching down below. It's not the only way to do it. That works just fine. And that is, we're going to simulate something called treadle. We'll come with this later. It's the one you're already using, by the way. We're going to execute a Chisel test, which you've also already been using. And then when we have bigger test cases, we're actually going to organize them with Scala tests, and we'll see that in just a second. Cool. Questions so far? Okay. So let's start thinking about how it takes to get going on tests, right? So first, like I said, what do you need to get started? Get that first test case going. However you can to get a test case running of any flavor, just get it working, right? Close that loop. So like I said, maybe you have to have manually human-generated inputs and manually human-generated outputs. So far, what we've seen, that could be, you randomly writing a few lines of, poke and then peek later on, or poke and expect, I should say, when you want to check the thing, right? But once you actually start getting going, then you start thinking about things like how to get coverage, right? So now coverage is what fraction of possible behaviors are you covering with your testing? And you want to kind of think about, okay, well, what are space of possible behaviors? How do I know if I've covered them? How do I measure this? And then have some sort of way to check it all. And then third and finally, when it comes to testing, you should figure out how you're treating the design. So in a lot of places, whether it be courses or even industry, you might hear the term black box or white box testing. Some people may not find those colors very informative, and so I think the terms opaque and clear are perhaps more obvious what's going on, right? So opaque or black box testing is we have the behavior the model is supposed to have, but we don't know anything about the internals. We write tests as best we can based on how it's supposed to behave. We don't know anything about what's going on inside. Clear testing, or white box testing in many people's parlance, that is, you know the internals, and you actually looking at the code and say, you know what? I don't trust this if statement. I'm going to try to make sure I cover both paths in the system. You're kind of making sure to kind of cover the line. And so it turns out when it comes to testing, they both have their merits, right? That the opaque style testing can often have very good coverage, and sometimes can catch certain areas you wouldn't think about if you looked at the code. If the designer who made the module, misread specifications and didn't consider a whole scenario, and if you made your tests based on the module, then perhaps you're also going to miss that too, right? On the other hand, the advantage of clear module testing is that you can sometimes have very fast convergence on coverage, right? Where if you're just trying to cover every case opaquely, maybe you take forever to get good coverage. And if you have clear model testing, you kind of get it right to the point, right? And so the answer, I kind of argues you should do both, right? That users, see the opaque module, and by users in this case could be somebody using your generator. you want to make sure you specify all those behaviors and do that correctly. Um, but there's definitely something to be said for if you know the internals, you can definitely make the test really get those kind of scary edge cases, right? And um, this perhaps brings to another point I should bring up, and that is when it comes to these testing of module, uh, the question is who's testing relative to who's developing. In the conventional, digital design environment in the industry, typically the people that write the modules aren't the same ones that test it. And there's both ups and downs to that, right? On the one hand, having that be differences of people is good because that way they are forced to agree on the specification, the documents in between, and that way they can see if there's any mismatches and they find it. On the other hand, it sometimes leads to less good results where the designers maybe are a little bit more careless when it comes to implementing modules. They're not the ones responsible for testing it. And then again, other people who do testing full time all the time sometimes don't have quite the same perspectives or quite the same things. And so as part of the Agile shift, there's definitely been a push towards having one person do both, right? They both design the module and design testing infrastructure with the module in mind, and they perhaps can do a better job integrating the two. And you actually design the module from the beginning to make it easy to test, which would be great. That being said, there's still times when you want to have kind of this outside evaluator, outside tester to make sure you're not missing anything. Cool. Okay, so before we start getting into code, I want to give some more advice about testing. Um, so number one, the goal is to automate this, right? So get humans out of the loop, right? Like I said, if your response is, oh yeah, I just run this program and look at the output, and if the fourth line is 10 and the 10th line is 12, I know they got the right answer. That's not an automated test. That's you just running a single instance, right? So humans are great for writing tests in the beginning, but eventually we want to have automation for the test generation. We definitely want to have automation for the test um, output checking, right? And making sure we have the right answer and what their answer is. And then finally, the actual comparison of the two definitely should be automated too, right? So we want to really automate as we can. Things like print statements and waveforms, those are great for debugging, but that's not testing. That's not automated testing, I should say. And then if it comes up, when it becomes clear at some point when you're trying to generate tests automatically that brute force is not possible, you can't do exhaustive testing, so you think, oh, well, I'll do random. Sometimes when you do random, you find it doesn't really get good coverage, right? It turns out there's just too many possible combinations, and that you run random for hours or days, and it seems like there's still bugs in there you're not finding, right? It's one of those times where perhaps having that clear box testing, you can definitely try the things. If you know how big certain numbers are bitwise in the hardware, you can make some inputs that are close to the maximum to try and trigger overflow or something. These are the kind of things that come up. So you may have to be a little more clever about random. And then also another thing you may see come up is assertions, right? So we use assertions quite a bit. We're going to encourage you to use assertions quite a bit. But assertions are one of these things that help you diagnose something is going wrong. They aren't really a replacement for testing, right? Number one, an assertion only monitors the operation of the module, right? It doesn't animate the module, right? And then number two, assertions usually check a specific property. They don't usually always, depending on what your assertions, check the entire occurrence, the entire result. They aren't usually comprehensive, right? So assertions are great, but they aren't necessarily a replacement for testing. One thing that comes up a lot, sometimes you have this time, we spend a lot of time debugging a bug, and that's often, as we all know, we spend the most time in our careers doing this kind of stuff, is writing modules and the hard parts, the hard to fix bugs that evolve over time. I've spent all the time finding a hard to fix bug. It's often a great idea to write assertions to detect the issue you overlooked before sooner. So that way, if this ever does reoccur, you can catch it, right? And for example, the last thing you want to hear in a project, whether it be hardware design or software systems, is you have a bug and you change something and it goes away. You don't know why it went away. You are not safe, right? that bug's going to come back. And so make sure you really get a root cause, understand what happened, and then you have an assertion to check that anything similar to that's going to happen again. Cool. Questions so far? Great. Okay. So as I said, I really want to kind of get folks excited about testing, not just at the end, but in the beginning when you first try to see if your first thing work. When you say close the loop, as I keep saying over and over again, that doesn't just mean get a small piece of design that's able to run, right? Get a small piece of design, get it to be able to simulate, test it, perhaps even push it through physical design, and even see how it maps to hardware, make sure you get that going. Try and get all the tools and pieces going, and then start adding in more depth to all of them, right? In terms of actually writing the tests, you can run them manually. We'll talk more about this later, and of course, something called continuous integration. That is, you have the tests automatically being triggered in the background, which is really nice. Um, and it's really helpful for a lot of things. For example, it's one thing if you have a project where you're really hard on it and you kind of manually test this code and you're pretty sure about it, put it online on GitHub, and then all of a sudden people on the outside like it, and then they want to contribute back and send you code. And you're like, oh shoot, how do I make sure the code is sending this pull request is safe, right? Well, if you have lots of testing available, they can do two things. Number one, they can make sure the code passes the test before they even upload the pull request, which is great. And then you can see that, and oh wait, they passed my test, so perhaps this code is safe if my tests are any good, right? And so if you find yourself in a situation where you're unsure about a code pull request because even though it passed all of your tests, that's probably a sign you don't trust your own tests, right? Which is not a good situation. And so yeah, you want to figure out what would it take, for example, if I had tests in my repo, so someone else made a code change and it passed all these tests, that I would feel comfortable accepting it, right? Like, well, what would that take, right? And then other times you can use testing is not just for correctness, it actually can be for things like design space exploration. Perhaps you're building a module, you make it a generator, so you have various knobs to turn, and you want to optimize it. Okay, well, I want to know for running this workload, how can I optimize performance or power or area? Well, using some infrastructure from your testing infrastructure, you can couple the two together, actually try multiple things at once and use this thing to execute it, right? So great. As you can tell, I keep talking about testing. I really want folks to get excited about testing early and often. It's kind of the whole point of today's lecture. I know in our homeworks, we deliberately have only given you parts of the test rather than all the tests. And it's because we hope you will write the test, right? Even our first homework, we asked you to write a test, right? So we really believe you guys should be writing the test. This class, like other classes and people have found, if you give students every test case every time, they tend to not write tests themselves, right? So we're giving you some of that scaffolding, but hopefully you'll write some of your own tests and get into it. And you'll see on the homework 3, which got posted, for example, that one of the things we do on the second part of it is to write that Scala model first. And with that Scala model, you can then test your design more concretely, more comprehensively. When it comes to testing, last thing I want to close out the slide is, think about testing. Like I said, we talk about getting involved in testing. And so like I said, don't wait till the end. Do it early and think about for this module, for this generator, what's it going to take to test it, right? And maybe you can change the abstractions or module boundaries to make it easier to test, right? If it's a module you're thinking, oh my gosh, like in order to test this thing, I need to have like all these things in the context and to kind of that maybe a sign your abstractions aren't quite right in place, right? And so think about that. Another thing that comes up in modules is sometimes you'll find that you can finesse your module boundaries so that you have purely combinational modules, which you can oftentimes are much easier to test. Sometimes you can even do exhaust testing on them. And then you have some other modules that are stateful, but perhaps if you have better bounds what that state's being used for, they're easier to test. So think about your abstractions, make it easier to do testing. And so, for example, in this course, in the homeworks, we normally kind of give you the module hierarchy because usually it's not enough time to build too many modules in a given week. But later in this quarter, when you do your projects, it's going to be your choice, your design, right? So you're going to have to think about, okay, what modules make sense? How can we make it easy to test and be composed? Maybe even get extra step farther thinking, okay, what modules could build first and then revise and expand or split later on for other modules to start kind of, getting bigger and bigger in your module, in your project. Cool. Okay, so what I just covered was pretty generic testing advice. Now we're starting getting more Chisel and Agile specific. So an obvious question you might hear with Chisel is we're all core talking about the power of these parameterized generators. And you say, wait, it's harder testing a single design instance. Now I have a generator which can generate many instances. Is that harder to test? Yes. Yes, it is. But I argue it's worth it, right? That, you can still amortize some of that testing overhead across that generator, across all instances. And hopefully we can also use parameterization to generate many tests too, right? So hopefully it's not insurmountable, this challenge, and I think it's worthwhile. In terms of what tools we have available, one of them is Chisel Test, which you've already been using. So yeah, there's a few other libraries out there, but Chisel Test I would say is the one we're most excited about. You may see something called Chisel Testers, which is the prior one. And to make it even more confusing, it's called Chisel Testers 2, and Chisel Test is newer than Chisel Testers 2, but that's the situation. Chisel Test is pretty nice. It's pretty smooth. And so how does it actually work? Well, you're writing a Scala program. This is a test bench. So the test bench is never going to be hardware. It's always going to be a Scala program. That Scala program then talks to a simulation of the hardware design to actually do the peeking and the poking, right? Um, and so as a result, there's actually choices in how you choose to simulate the design. The one we're using in this course, and I think you can get by the entire quarter with it, is something called Treadle, which is a Scala implementation that directly executes the internals of your hardware, right? So you may remember from earlier, I mentioned Fertile is the name of the IR for Chisel, the actual hardware representation. And so Treadle is something set directly in Scala, so no need to compile anything. It's already a program running. It's kind of like an interpreter. So it's very fast startup time. And for small to medium-sized designs, it's actually pretty decent. Now, if you have a very large design, it's going to be slow. But we don't have very large designs in this course. So if you have a large design, what do you use? Well, I really recommend Verilator. I recommend it in a lot of ways, right? So number one, it's open source and super fast. The price of it is you have to kind of do a few things. Number one, it's a compile ahead of time simulators, right? It's AOT, right? So you have to take your design, turn it into Verilog, get the Verilog to Verilator, have Verilator generate with plus code, and you can compile it with plus code. So that takes more time to get an actual simulation started. The other thing about Verilator is it doesn't just work, right? So Treadle, you can just say, oh yeah, you're running a test and boom, you're running. You're not really worrying about, connecting to it. With Verilator, you need to build a harness yourself. You actually need to build a harness to talk to your design after Verilator has gone through it. Now, the good news is once you've made the harness, you can reuse it because usually design, even though it changes and change the harness interface, but there's still a little bit more of an overhead getting going, which is why it's not usually kind of the default thing for a lot of stuff. But there are other simulators, right? People in the industry often use VCS as a common synopsis tool, and that works just fine with Chisel generated Verilog, and it can also, of course, talk back to Chisel tests if you want to use that for your test bench. For my own personal group's research, we have something called Essent, which is a other Fertile simulator. It's like Verilator, it takes in the RTL, but also with plus code is optimized. Ours has even higher speeds than Verilator once it's running, but there's also a substantial compile time price to be paid. So for this course, for simplicity and just no compile time and just ease of use, we're using Treadle, but these other things exist. Cool. So let's actually look at some code. Okay, so we want to test a combination component, right? So what's nice about it is it's stateless, right? It's a pure function. Whatever inputs we give it, that directly influences the output. So what that basically means is that each cycle is independent, right? So I can kind of do one test per cycle, and then there's zero concern about the prior tests, right? Versus you just stateless explosion with sequential things about okay, what did I do last cycle versus this cycle, and it kind of blows up. With stateless combinational stuff, you can kind of more directly approach it, right? So what do you consider? Well, first look at the inputs, and in the most obtuse general case, you could consider every input independent, but this is one of these cases where perhaps having some knowledge of the module, right, having that clear box mentality, um, you can know, what, these two inputs, they don't need to be, we only consider all possible combinations, right? It's okay, we can do just one of these, and that might be okay. Right? You can kind of think about what makes sense. There's something about generators. You might start asking yourself, okay, what generator parameters should I be considering? And then, of course, as you start actually trying to run these things, how the generator parameters as well as the inputs impact the size of the input space you're trying to test, right? Now, if you have a small enough, simple enough module, you may be able to get away with exhaustive testing, which is pretty cool. You can just say, hey, I tried every possible combinational input, and they all passed. So that's pretty cool. And that's not always possible. And so the things you can consider. Sometimes you can make the parameters for your design small to exhaustively test, not as necessarily small to be useful, but small to exhaustively test, and then maybe you can scale them back up and do a few points to make sure making bigger didn't break it. There's things to consider for that. Okay, so let's try something out. So what are we gonna do? Well, we're gonna go back to number representation. In this case, sign and magnitude, right? So sign and magnitude number, is some number of bits for the actual value of the number, and then we have a bit 1 or 0 indicating the sign. So sure, we can define a class for this. Actually, it's a bundle. Great. So actually really want to test is not just representation, we want to test an adder for this, right? So let's go ahead and take in two of these sign and magnitude numbers and produce a third one. In this case, they all have the same width, so this is a truncating addition. And so here's an implementation of the adder, right? So what do? Well, we say, hey, if they have the same sign, we can just set the out sign equal to the input sign, either one because they're the same, and we just add the magnitudes. And because we use the plus sign, it does the right thing about truncation, and we're done. However, let's say they have different signs. Well, um, what do we do? Well, if one is a larger magnitude than the other, we can subtract the smaller one from the bigger one and use the bigger one's sign because it's not going to flip the sign to the bigger one. And if that's not true, the other case, then we subtract the other way, right? But I hope, this is correct. But if you're looking at this and you're like, you know what? I'm not sure that's right. Great, let's go ahead and test it. That's the whole point of this, right? Let's go ahead and build some testing. So here we are, day one. Day one, you're going to write manual tests, right? So you're going to manually envision some inputs and manually envision the outputs. So let's say I'm going to add one, positive one, because it's zero for false for the sign bit, plus positive two, zero for the sign bit. And well, we better see 1 plus 2 equals 3. Woo! In this case, field test succeeded. If it doesn't match, there's going to be an assertion violation. So one thing I often do is if I don't trust my test setup, I might deliberately break it, make sure I see what errors look like, and then go ahead and fix it. Cool. So that's our simple human-written manual test. Great, but that's one test, right? And I don't want to write a bunch of these. So what can we do to make this better? Well, first we're going to make a model, right? Something to tell us what the correct answer is. And so like I said, we're going to use Scala to get the correct behavior. A lot of times this is pretty easy, right? So yeah, you can just write real programs, heck, even use var if you want to or something sometimes. And you can usually do the same functionality in far fewer lines than you would in Chisel and hardware because you aren't trying to build a full generator. You aren't trying to optimize a hardware design for pipelining or anything. You're just getting the same functional answer. Now, this one looks perhaps a little more complicated than you were anticipating. That's because I'm trying to make sure we capture the exact same behaviors for truncation and wrapping, right? And if we're going to be comparing numbers, we got to make sure we're careful about that, right? So for example, in this case, because we're working on Scala's integers, which are a signed 32-bit int type, we need to make sure that the model we're working with actually conforms to that, right? So we're saying, hey, we don't know how to do zero width. Also, we actually don't want 32 bits because we need that signed bits. So we actually only want to do 31 bits and less. Okay. So how do we go about doing this? Well, we're going to go ahead and make a mask, which is, all ones in the bits we expect to have. So this code snippet will produce, W1s on the right side of the number. And then we can go ahead and AND out the sum to get the resulting bits, right? So the sum, of course, we just add them together. This all looks hopefully straightforward. And then the question is, what's going on with this funny business in the middle? This is the truncation effect on a negative number. So what we do is, if you add these two numbers together and the result is negative, okay, we need to be a little more careful. What we're going to do is we're going to, if it's negative, we're going to make it positive momentarily, truncate it, and then make it negative again. So still negative results, right? So you can see this is still negative, negative, actually cancel each other out. The reason why it's not unity, it's not doing nothing, is because in the middle we did this masking to get the truncating effect. But this works, right? So if I do, 4x4, this all works. If I was to, for example, not do this truncation stuff, and I just said, yeah, return sum and mask, it's also going to seem to pass, right? Now, but what happens if I start getting the truncation effects, right? Okay, so let's do the math. 4 in binary takes 3 bits, right? Maybe it's not a good example. What if we did, how about like 7 and 7? 14, okay. That's not technically truncating. 14 is less than 15, so it fits in 4 bits. What if I do in 3 bits, which can hold 7, but it can't hold the answer? Is that the right answer? I don't think so, right? Not just from truncation, right? And so, oh, sorry, I still the mask being applied. We're not even doing the truncation. Sorry, I should just say sum. Sum, right? So at this point, we're not modeling truncation effects, right? And then we put the mask on, then we do model truncation effects. Ta-da! But this only handles a positive case. That crazy code I commented out handles a negative case. It doesn't always need to be so complicated. This is just in this case that we have signed numbers. Usually in hardware, we have unsigned numbers. And I want to make sure that truncation just right. Hopefully I convince you that this model is correct. Sometimes you have test cases that are just for the model, not even for your hardware design, to make sure your model's correct, which is an important thing to do. Cool. Questions so far? So we had our chisel component, we wrote manual tests, we have a model. We're there, almost. A few more levels of abstraction to go. So what do we want to do? Well, just because of a model, we need to somehow combine the model with a instance of design to actually compare it to, right? And so what we're going to do is we're going to make this abstraction here, which is as labeled here, test add, right? So what does test add do? Well, it's going to go ahead and given a instance of this adder and some inputs we want to test, it's going to go ahead and perform the operation, right? So it's going to go ahead and put A and B as inputs into the module, right? So notice how to correctly set the inputs to the module and also recognize, okay, is this negative? What's the absolute value for the magnitude, right? To get a sign magnitude going in. And then, of course, we want to make sure we get that right result. And so at the end, we're going to say, hey, when it gets to the result at the end, I'm going to talk the middle portion later. That's just printing the result. But actually comparing the result, what do? We need to check the sign and the magnitude, right? So the sign, well, based on what the model tells us, the model doesn't actually do sign magnitude. The model just adds with the truncation effect. And if it's negative, well, that means we should have 1 for the sign bit. Okay. And for the magnitude, right, same thing. We're going to go ahead and use the model and then see its absolute value. Okay. A few more things going on here, right? So first, we're looking at this not equal to 0 and my comment next to it. Does anybody know what's going on with that? Why do they have to do that? Well, let's try and work backwards. Okay. I'm only checking the sign if the result's not equal to 0. So in other words, if the result is equal to 0, I don't want to check the sign. So why do I want to check the sign if the result equals 0? Almost, right? So the answer is with sign and magnitude, because the magnitude and the sign are different portions of the number, um, you could have two zeros. You could have a positive and negative 0, right? Which, yeah, that's, to most of us, we're like, wait, why would I want that? I don't want that. Um, Interestingly, floating point does have two zeros intentionally because people like that for things about limits, right? Oh yeah, I can converge from which side I can converge from. They actually do want that. But in the general case, no, we want 0 to be 0, right? We don't want two zeros. And so, yeah, in this case, because 0 could be positive or negative, we're just saying, you know what? We're not going to check the sign bit on 0, which maybe that's a bug in our test, right? That's why I put a comment there. Because it's like, it's one of these things where sometimes it's good to do testing like this. You start doing testing, you start realizing, oh my gosh, there's some corner case I didn't think about. And what does the specification tell you? My specification might mention this. Oh shoot, we need to figure out what is the correct behavior for a module for this. And we need to write this down and then make sure test cases enforce it, right? So maybe you might decide as a group, you know what? Even though combinatorially it's possible to express a negative 0, we're going to disallow it in our hardware, right? This test case is making the implicit assumption that if the magnitude is 0, the sign bit doesn't matter, which maybe it's an okay assumption, but these are things to kind of be clarified if you're testing. The rest of this stuff is me doing some pretty stuff to print out what the test case is doing. So I can kind of point out, hey, the input, is this and the output is this. And then what's going on here? Well, I'm using that string replacement magic. So I'm going to print out the sign if there is one. So you can see if it's negative, I put a negative sign. Otherwise, I print nothing. And then the print the magnitude. Now, this is something you may not have seen yet in the course. So you often hear us talk about these testers say peek and poke, right? Well, normally you poke first. You send an input in. And usually so far it's been poke and expect, right? Poke some inputs in, look at the output of expect. Peek lets you read an output. However, the value you get is a chisel type. And you need to make the leap back to Scala land to actually do math on the way you expect to do math. And so in this case, we are know that this happens to be a chisel Boolean. So a chisel bool, so we're converting this to a Scala Boolean. There's a similar method for if it's a uint, you want to get an int out of it. Cool. hopefully this still works. It does, right? So you can say, yeah, we passed in, 2 plus 3 and saw the answer was 5. So um, what's pretty cool about this is we built up this abstraction now. Now we have this ability to say, hey, I want to test my adder for a given 2 inputs, a given width, and give me the adder instance. I can even also control if it prints out the test cases. So by default, I'm printing the test cases out one by one. In future slides, we're going to do so many tests, we don't want to have to print out anymore. We're going to turn it off. That's kind of cool to have ability. But I want to kind of pause, appreciate what we've done here. We built up an abstraction that's kind of a reusable component, right? Where we had a model. Now we've automated the interaction of the model with the design. It's actually like a test case interaction, right? We have given the details of a test, it's actually kind of manifests that test. So in order to make more tests, I just need to give it, inputs and a width and an instance, right? So you can see I can keep making more lines like this and keep making more tests, right? Go toss down another one of these, no problem, and make another test, right? So I want to do, yeah, maybe let's see if we want to push the negative boundaries, right? Let's do -7 plus -7 and 4 bits. Hey, it still works, right? So it's pretty cool. So it's kind of points. You can see here we are building up infrastructure, and you can see infrastructure at this point is actually already starting to kind of compare or even exceed in terms of line count the original module, right? Original module was, not that long, and now we had a model. We have this automated interaction. That happens. But the good news is we're starting to get increasing confidence in our module, right? We're getting this more rigorous testing. Cool. Questions so far? Yes. Yes, it converts a uint coming back from peak into, yeah, to repeat the question, yes, if you go into the module with simulations through Chisel test, the dot peak will give you a uint, and this converts it to a int. Correct. So to be really clear about when to use this, this is something you use in the environment of testing on an IO of something you're simulating. If you call .lid value on a uint inside of your design during elaboration, I don't think that's going to work too well, right? Because the uint doesn't have a value yet. Because remember, at that point, uint is just an abstract type. It's not really hardware or anything. And so this is more when you have hardware that exists in simulation land. It's a way to kind of peek at it of what this is. But yes, that's what it's for. Cool. So yeah, here we are kind of building up abstractions. So you can see now we have the ability to kind of, given stimuli, quickly do a test case and actually, sets up the inputs, checks the outputs, and even, interacts with the model. We're not quite there to a full test automation suite. Now we need to figure out a way to actually generate the test cases, right? We did kind of steps 2 and 3. Remember we talked about test cases, you need input stimulus, correct answers, and automation. Up until now, we kind of had correct answers with the model. That's number 2. We had automation with this thing we just built here. So number 3, we didn't have number 1, which is the stimulus generation, right? So let's do that. For this thing, we could build a really simple one and just do exhaustive, right? We can just try all possible combinations of numbers, right? So given a target width, we could go ahead and do this, right? So we can say, hey, I want to test a given width. So I'm going to go ahead and instantiate an adder of that width. We know for a given width what's the biggest number represented binary. That's what this tells you. So you can say, hey, using Scala ranges, I want to get from negative that to that. For both numbers, we're trying all possible combinations. And we're going to go ahead and run that with the thing we just made. And we're going to turn off the printing. That's what this the verbose is, because we don't want to see tons of stuff printing out, right? So if we go ahead and run this, uh, it defined and it ran, and because there was no exceptions, we didn't even notice it did it, right? But maybe if I go ahead and turn verbose back to true, we can kind of see the test cases it runs, and oh my gosh, right? Who could have thought that a simple 2-bit adder could have so many test cases? But it does, right? Because we're comparing um, two 2-bit inputs, right? So it's already going to be 4 bits of input. But then because the width refers only to the magnitude, there's also the possibility of a sign. It's like we're actually adding like 2 3-bit numbers, right? So 6 bits of potential input or space we're toggling. So yeah, you can see it kind of blows up in a hurry. Yeah. So the first line does not give the correct answer, or not the answer we expected. It's not -6 because it got truncated. Yes. But you can see, right, this is actually doing quite a bit of work. Here we're doing exhaustive testing, like I said. So if you know more about your module and the properties, maybe you don't need to quite do it this way, right? For example, one obviously might be, well, if you exploit symmetry, right? If I do A plus B, do I also need to do B plus A? Maybe not. So you can imagine changing these loops to half the iteration count to basically do less than in there. But you can see, yeah, for small, that ran almost instantaneously, so that was pretty cool. Why don't I go ahead and set this to false so it's quiet, and we can do a bigger one. Let's try maybe like 4 bits, which, yeah, that was pretty quick. Remember, so it says, we say it's 4 bits of magnitude with a fifth bit for sign, and then 2 of them says 10 bits. So in other words, 2 to the 10 or 1,000 test cases we just ran, right? So from prior experience, I think I can get away with 8 before I get tired of waiting for it. It's gonna take a few seconds. So we're gonna let it run for a while. But we can appreciate how long this is, right? So we said 8, add 1 for sign, then times 2, that's 18. 2 to the 18, that's 256,000 test cases we just ran. And so yeah, it took, 20 seconds, 10 seconds. Um, remember, this is running with Treadle at Scala Simulator. If we have a really, really big design, of course, we could run it even longer with even faster with Verilator. But this kind of shows you what's possible, right? Here we are doing exhaustive testing, which is one option. It's possible for sometimes very simple modules, but that's cool. So at this point, it seems pretty simple, right? And I would argue in this case, we had a pretty good use of abstractions where we had, in this case, this piece of code focuses only on just generating the test space. And given the stimuli, it trusts this module to do the right thing. This module, given stimuli, talks to the designer test, and it compares the output to the model, and it trusts the model is correct. And then of course we have the model, which hopefully we got convinced by some other way it was correct. So perhaps you have test cases just for the model or something, but you can kind of say we're building up abstractions, right? So it starts off with a model, so that way we know what the right answer is, and then we automate the interaction, and then we perhaps in this case also automate the generation of test cases with that model. Cool. So we waited for 8. If I did 10, it's not going to finish too long. It might actually finish. My fans might heat up. They're already going right now. I think you can hear them. Maybe I'll turn it off before it takes too long. Use my battery, but you can see where it's going. Oh no, it's not going to stop. It's not an M1 Mac. Yeah, it's gonna have a fun time. Okay, let's see if we don't break the JVM in the process. This is fun. Um, but you can see, eventually combinational brute force, not gonna work. So we can try random, right? So here we're just doing uniform random. As I mentioned earlier, you may want to consider more directed random. So how does random look? Well, given a instance and a width, it just picks 2 numbers in the right range. Oh, sorry, I didn't read my own code quickly. I generated a function here that generates an input, right? You can see what it does, right? It does this. Now, we discussed earlier that in Scala, if you have a function that takes in no arguments and it doesn't change anything, you can call it without using the parens. Here, I deliberately included the parentheses to make it clear this is a function I'm calling rather than just some value floating around the code. That was a style choice. But yeah, so here we've made the ability to generate 2 random inputs, and then of course we can run that repeatedly in a for loop to see if we want to do how many trials we want to do. So hey, if you want a 4-bit thing, 5 trials, yeah, no problem. I myself might have a thing burning up though. Yeah, okay. Well, we learned that I shouldn't do a combinational one and leave it running. Let's go ahead and restart the. I'm just gonna do that. It's okay. Yeah, this is local, so this other stuff should reload pretty quickly. Knock on wood. Yes. Okay, and then we have to load in all these things: the sign and magnitude, the test case. So that one's actually not required, I guess. Our model, our ability to use the model, and then we can either do exhaustive, or as we just were doing a second ago, we can use that same functionality we use for the exhaustive to actually do that for the random, right? So the point is, here we built up abstractions, and we're kind of using abstractions kind of programming to build up a more sophisticated test case, and hopefully random still works. Yes, it does. And because we didn't say verbose equals false, we can see what it's printing out, and we can see, yeah, these are totally random inputs, right? And if I run this again, we're gonna see different numbers, right? Because we didn't see the random number generators. It's actually just, changing. Now, sometimes the random you may choose to see the generators, so that way you can be sure you can kind of get reproducibility for debugging something, but that's another conversation. Cool. Questions? So yeah, so that was the combinational test. So let's go ahead and talk about starting to structure stuff. So we just saw right there, we had a very particular use case. We had one module, and we kind of built over these functions and libraries to eventually call some function. That one function, by calling it, did a lot test for us, right? Whether it be the random one or the brute force one. But oftentimes you still have more organization to incorporate, where you have multiple modules each have their own tests or other things. And so we actually use something called Scala tests. So sometimes students get confused about the difference between Scala tests and Chisel tests, and the answer is we're using both. And Chisel test actually even depends on Scala test, right? So Chisel test, as we know, is a thing that's going to handle instantiating a module, running a simulation, having our test bench talk to the module, with peek, poke, expect. Scala test is a way we can do to organize multiple tests together. And it's cool if you use Scala test, it's a nice library. SVT is aware of it. So SVT can go ahead and, you say test, it knows to run Scala test and that kind of stuff, right? Now, when you run tests normally, the test command in the SVT console, it tests all tests it can find. If you only want to run a specific test, there's a test only command. The thing I actually do most often, even though I'm normally a command line person, in IntelliJ, if you're looking at the file with the test cases, you can right click on the test case and say run this test, and it runs that test with a little green triangle for you to do that. So it's kind of very convenient. So cool, let's go ahead and look at some examples with Scala tests, right? So for example, here we are using Scala test in combination with Chisel test. And you can see here we've made a tester with that. So that's what this is. And so we can go ahead and give these tests some names. So this may not look like code, but this is Scala. We talked about how with Scala, you can sometimes avoid the need for, dots and open parens and arguments. You can chain together things. It looks a lot like written text, right? We have spaces. So these are actually all operators being put together. We can say, oh yeah, this is the behavior of, in this case, actually you can parameterize the name of the module. So often it's a static string to indicate the width. Here we have two manual test cases, right? So we say, hey, I want to do this simple test so I can describe it. Okay, it should, and this can often be maybe English describing, handle this corner case correctly in a certain way. Internally, of course, we were calling test. And now we put this all together, we can go ahead and run this, right? So usually you don't call this command. Usually you do like SBT test and it does it for you, but for Jupyter, this is how we're doing it. As you can see, because of the nice test library organization, you can see how it kind of groups together. Okay, this thing we're testing, behavior of, and then each test kind of has its own line. And you can see the green, yes, it's working. It's actually going to be hard for me to break these because if I change this input, it's actually going to do the right thing. So I have to go inside there to actually break it. But I think you guys get the idea. This is what we use in this course, right? The only other wrinkle on top of this is we have some additional stuff built on top of both Scala tests and Java tests to do auto grading, but not worth the lecture time. About auto grading. um, and so, yeah. So as you see the slide, we love working with bundles. And bundles, maybe you don't want to peek and poke each field individually. Maybe you want to poke an entire bundle at once. So this feature is technically been experimental. Even though it's technically been experimental, the next version of Chisel is going to move it out of experimental. So as far as they're concerned, it's basically ready. And it's a way to create a bundle you can start passing around and connect to things, right? So you can see here, maybe it's better if I put a new line in there. Actually, maybe it's better if this is 3 different ways of expressing a bundle of a sign magnitude number. And so, yeah, it's pretty gnarly in my opinion. But this is kind of 3 different ways of doing it. And once you have one of these bundles, you can go ahead and just poke that bundle, right? So for a single instance, maybe it's not working. Maybe you have multiple lines. But if you have the same bundle input you want to use multiple times, maybe it's worth using one of these bundle literals to kind of have that thing handy to pass around. So looking at this bundle literal for just a second, what is it? Well, really you need the bundle somehow. So perhaps this one's the most clear one, right? Um, and then you call dot lit, and then you do this weird syntax where you're using the wildcard replacements, but these are the field names, and these are the values you want to assign them. Um, yeah, I find this a little bit gnarly. I think there's still some room to improve this syntax. To me, it feels a little bit too awkward. This is a kind of example of embedding as opposed to being a native language, but that's the situation. In terms of what goes on the left side over here, to me, the most intuitive one is declaring the bundle type, right? I want a new sign magnitude of 4 bits. It's actually not what's recommended. What they recommend is actually this reflection technique where you can probe the type that is at IO, and that way you're guaranteed that the types match up. So I can say chisel type of, and then in this case, give it the IO field, and it's going to guaranteed to match the types. And then that type hopefully corresponds to what you're trying to set over here. Now, the reason why they recommend this approach is that, if you have a type, your own class, different parameters can suddenly change the things, right? So it's kind of up to you to make sure that this parameter and this thing is what you intended, but it's kind of this risk of duplication, right? You have your declaration here, and we're actually declared elsewhere in the IO. By using this reflection technique, it's a dry principle, right? Don't repeat yourself. You're using declaration from the IO, and that way you're guaranteed the types match up. So that way, this is supposed to be better, and I would say technically it is. But yeah, me reading it, this is still pretty gnarly. So maybe it's more clear that I'm making a bundle of a certain type. But you can kind of see both approaches. But yeah, we can go ahead and use this, and hopefully it works. Yep, cool. Questions? Okay. Well, then we're ready to leap into the sequential example. We'll see if we finish this today. So sometimes a little bit long. Um, so we did the combinatorial example. And for that one, I built up abstraction after abstraction. And we kind of showed, yeah, we could do exhaust testing, we could do random testing, we kind of do arbitrary manual testing. That gets a lot harder with sequential components, right? Sequential components have memory. So your prior input history interactions matter, right? And so there's a huge state space explosion, right? And as a result, almost always exhaust testing is impossible. And so you kind of have to be more clever about this. So for today, what are we gonna do? We're gonna take that Q module we played with last time, and we're gonna build a tester for it. And so last time we had that kind of test module using to kind of just animate to show it doing certain things. Now we're actually gonna try and test it, right? And so as a reminder, right, a queue is like a FIFO, first in, first out. It has memory. It remembers what it's seen in the past, and that's why it's able to kind of reproduce it in the future. It has a decouple interface on it, so we're going to use that decoupled example. In particular, the variety we're going to have is one that has the pipe set to true and the flow to false, meaning if it's full, I can still enqueue at the same time if someone's dequeuing. If it's empty, it still has to wait once they're going through it. Okay, so the flow equals falses. All right, let's go ahead and see this. Well, step one, we need a functional model of this queue. So we're writing this in Scala. And this one's thing you gotta be a little bit more careful, right? If you have something where you just care about the combinatorial numerical result, that's pretty easy to write in Scala. In this case, we actually want to get the timing behavior, right, over multiple cycles, how it behaves over time, remembers things. You need to be a little more careful. And the reason why is that we kind of have contrasting timing philosophies. In hardware, the way to think of it is it's kind of like everything happens all at once, combination logic processes, and then there's kind of this, synchronization point of the cycle, which, defines when register's memories update. So it's kind of, a bunch of stuff happens, but it's kind of, waiting, and then all at once a bulk update, right? And so in other words, if you change the value register, you can't see it until next cycle. Meanwhile, in software, typically in language like Scala, it's this imperative, line by line kind of code. We're doing many state changes in a row, right? And so as a result, I do one operation, that results immediately visible next line, right? So if you're not careful, when you're writing a model for a hardware component, you could have a register update, and it can appear to update too soon, right? Basically, if you read the result too soon, it's like the register didn't have a cycle delay, right? And so you gotta be very careful the way you order these statements to make sure you're kind of being faithful to the timing behavior. And so you can kind of see my easy fix there, which is if you have a register or you're trying to model the behavior of a register, make sure everybody that's going to read it reads it before you modify that register for that cycle. And if you can do that, you're going to be fine the vast majority of the times. Now, sometimes it's hard to guarantee or you can't do that. Then you go to the next line, which is the alternative, and that is you make two variables for register. One is the value you let people read, and then one's the one you update for next value. So it's kind of like register and register next. Let everybody re-register, and then at the end of your simulation cycle, then you do register next in the model. So you gotta be a little careful with this kind of stuff. So for example, in our queue model, right, for the actual queue, guess what? We're gonna use a Scala queue. That's easy. We're gonna use a mutable one just to make our life a little bit safer here. So we're having a mutable queue. Okay. Alternatively, we could choose to have a immutable queue and then have a var pointing to it to kind of keep overriding it. But I like this way better. So we have kind of the DQ ports and the NQ ports. So same thing, right? If you think about it, the DQ port is kind of like you're reading from the queue, and the NQ port is kind of like you're writing to the queue. For that reason, I did the DQ stuff first, so that way we can kind of read the contents before we write anything new in there and make sure we don't get that timing behavior wrong. So for example, we're saying, hey, initially our DQ is not going to be ready because there's nothing in there. However, we can change this as needed. Sorry, the DQ ready set, this is actually an external value. So even though it's a var inside the queue model, we want someone externally to come set this when they mean to set it. If we have anything to output, that will depend on if our queue is empty or not. And then if someone wants to dequeue, they actually need to call this function. This is the equivalent of if fire, right? If our DQ is both ready and valid, we'll give them that result. Otherwise, they're going to have nothing, right? And so here we're actually using a Scala option to indicate the fact that the queue may not be able to return anything. Meanwhile, on the NQ side, what do we have? Well, are we ready to NQ? Well, either we have room in the queue, or we're full and someone's trying to DQ. Remember we talked about this, pipe equal to true parameter. And then someone's gonna call this function attempt to NQ, right? So they're trying to give us an element. So we're in this point, we're kind of assuming our queue is taking ints. And hey, if are we able to NQ? Great, we're gonna go ahead and put this inside of our queue. So this is a Scala model for our queue. Okay. And so here I am doing some manual human ridden test cases, right? Day one getting started. So we instantiate a queue. We attempt to, push on one. So some of these things don't have any impact internally, but we still call them just because we want to have the same kind of structure for both. We're going to say, hey, we're not ready to DQ. So it's not going to push anything out, but we're going to go ahead and NQ to one. All right, so we push the one, and then on the next cycle, we're going to say, you know what, let's go ahead and push two and pop the one. Okay, so we're going to go ahead and try to do all these things and see what happens. You can see, yeah, it goes through. And then eventually, we are attempting the DQ down here. The result, of course, is going to be we get the value back out. So yeah, there's quite a bit of stuff here, but big picture, right? We were very careful. We wrote a model, and we were very careful to get our ordering between our registers and our reads and our writes. And then we have a model, and he redid a manual animation of it. Cool. Questions? Yes. Yeah, the DQ. Remember, if we go back to the prior slide, good question. The NQ doesn't return anything. It's a unit. This is equivalent of like a void. So there's no return. And so yeah, that last line comes from the DQ, correct, of the option type. Okay. Yes. 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 Yeah, yeah. So the critique is, we were talking about trying to use our model to make sure we're correct, but of course we need to make sure our model uh, is itself correct. And so in order to do that, how do we know our model's correct, right? If it's a really simple model, yeah, we get to look at it. Hopefully, we got it right. But with a more complicated model, um, hmm, we mentioned that before when we talked about, yeah, maybe make test cases for your model and make sure it's right. But yeah, something like this, you probably want test cases for your model before you even worry about your model interacting with your chisel design. But bigger picture, yes. If you have a more complicated sequential Scala model, it can be hard, right? And so we're dealing with our research project right now with this big, complicated cryptography accelerator we built. And yeah, we are currently paying technical debt right now, where we are refactoring it. It's basically a situation where some of our modules are extremely hard to test based on the way they're currently written. And kind of solution is to think about just what we spoke about. Well, can we renegotiate what the module boundary is, not for physical design, but for an abstraction that's reasonable for me to test, right? Is it something that I can write as a convenient function to test, or is this a really complicated interaction? And we're trying to change those boundaries. And sometimes I said, sometimes difficulty in making a model or testing the model is a sign that your abstraction is too hard. And guess what? If your abstraction is too hard to model and test, it may also be too hard for you to get correct in hardware. There's a handful of cases where it's easier to write the Chisel and it is to write the Scala model. There's a handful of cases. Most of the time, if your model is hard to write, your Chisel's even harder still to write. So that's a good thing to be concerned about. Yes, correct. The register behaviors. Yeah, yeah. Okay, so repeating the question, as you know, in the prior slide, I encourage people to call DQ before they do NQ to make sure we do the read before to write to a register. How can I do that in a more disciplined manner for a larger design? I don't have an automatic fix for that, no. But um, you're right. This is you see the challenge here. And the point is, as I said, this is a challenge. And just because, let's say we don't do Scala or we don't do a model-based testing strategy, the problem's still there, right? Still the problem of how do I have a automated way of generating the correct behavior of this module, and how do I have a way to convince myself that my automated way of generating that correct thing is correct, right? Now, who checks, who watches the watchers, right? It's another expression for that from sci-fi or whatever, right? So this is exactly that scenario. And you're right. At some point, you have some combination of testing testers until eventually you get down to some sort of base case you believe to be reasonably simple to convince you got right. Um, yeah, I would say testing is not an automatic thing. It's definitely more of a thoughtful thing. That being said, if you look on the internet and see people talking about Chat GPT, people are really excited using Chat GPT to write test cases, right? And so my pushback to that would be, um, if you use Chat GPT, don't use it to write a test case. Use it to write a test case harness. And then, as we talked about, how ways to synthesize multiple tests, right? Because, yeah, if you think it's really tiring to write many test cases, there's not a very high value test, right? You want to have that more automated interaction, more automated test generation, and get ChatGPT to write that harness for you. Okay, so I'll take more questions. Yes, go ahead. Yeah, I'm gonna go ahead and repeat that for the recording and summarize it. The idea is, what if you had a step function as some sort of way to um, capture a notion you're requesting an NQ, requesting a DQ, but then somehow waits to actually do the actual execution, make sure we do it the right order. Yeah, I think you're right. I think as you're speaking that, I had a similar idea. We made it some sort of class for ourselves. It was a wrapper, this is a register around a Scala type, and that way we can guarantee that, that the dot next value is not visible until we want it to. Um, I think you're right. I think you have the right attitude totally of what abstractions can I build that are testable, confirmable abstractions to make this thing a more manageable complexity of what I'm dealing with. That's exactly the right mentality. I think your sub function is a good idea. Perhaps this register model class is also maybe not a bad idea, right? You can imagine some sort of generic Scala type where you can give it a Scala value and you can say, you can call dot next, so you tell it the future value, and then at the end of your code, you update the value or something. Yeah. So that's one of the things, critique is, isn't that just civil? Yes, but I mean, part of the thing about testing is you want to make sure you have enough difference in the manner in which you're doing something, you actually find something right. If you find yourself like writing Chisel and then copying and pasting that code and changing a couple keywords to make it Scala as your model, probably not a very rigorous model, right? You want some difference in the way you're doing things, right? And so um, if you have a choice between options of implementing something, maybe you pick the one that's not the way you did it for the other case. That would make sure you have some sort of orthogonality to it that you have a better chance of better coverage. Okay, so we're out of time. We have a couple more slides left, so I'm gonna go ahead and start with those on Friday's lecture, or Wednesday's lecture, sorry, I'm spinning around, the next lecture, and then we'll get on to the following lecture's content. Cool. Have a good day, folks.